그러면 which problems we want to challenge?
We would like to challenge topic 14, water bottle rocking.
14. Michelle, say.
We extend the challenge.
Step. So 5 minutes for preparation. Why is it in empty space?
I can start my report now. Okay. So, good morning, honorable judges and competitors. This is a reporter Xu from Team ND Joker, and today I'm going to present problem number 14, water bottle rocket. And this is the outline of my presentation. This is a problem statement. Pump air into a plastic water bottle partially filled with water. Under certain conditions, the bottle is launched and flies into the air. Investigate how the acceleration during liftoff depends on relevant parameters. And our main focus on this question is the successful launch conditions and also the relation between acceleration and air pressure or water volume. And this is a demonstration video. So after we pump air into the water bottle, we can see that the water bottle rocket flies into a very high height. And now I'm going to talk about the theory of this phenomenon. So the whole process of the flight of water bottle rocket is divided into two phases. The first one is the water jet phase, and the second one is the air jet phase, which is after the water jet phase finishes. So first, I'm going to talk about the water jet phase. So according to the law of momentum and impulse, we can find the thrust, which is the force given by the water for the rocket, and it can be expressed with this equation over here. And if we change this equation, we want to express the equation using the mass flow rate of the water, which is over here. The Q over here is the mass flow rate. And after we have this equation over here, we also want to calculate the velocity, relative velocity of the water to the water bottle rocket. So we are going to use Bernoulli's equation to calculate the value of VE. And also, according to mass conservation, we can substitute Vs into this equation. And then we can calculate VE, and it can be expressed with this equation over here. So we also consider that the mass of the rocket will change over time because the mass of the water inside will change. So the total mass of the rocket can be expressed by the sum of the mass of the bottle and the mass of the water inside, which will change over time. And combining the force given by water, the air drag force, and also the gravity of the rocket, we can get the acceleration for phase 1 over here, which is the expression below. And now I'm going to talk about phase 2, which is the air jet. And we define the air jet, the start of the air jet, to be after there is no more water inside. This is the start of the air jet. So after all of the water is out of the rocket, then the air inside the rocket will have an air expansion. And this air expansion is very fast, so we consider that it is an adiabatic expansion because it is not enough time for energy, for heat loss. And the rocket will accelerate until the pressure in the bottle is equal to the pressure of the environment. So here we can calculate the force given by air expansion for the rocket over here. And we also define the mass flow rate of the air. And as I mentioned, we consider that this is an adiabatic process due to the minimal time for heat exchange. And this is the equation for adiabatic process. So now we have these equations, we can calculate the acceleration of rocket in phase 2. So combining the force given by the air expansion, the air drag force, and also gravity, we can get the acceleration for phase 2, which is shown in this equation. And here comes our experiment. This is our experiment setup. So we have a pump, a launch angle, a power rocket, and a launch pad to make sure that it is vertically launched. And we also use Python simulation to get our theoretical data. And also, because of the limitations of the camera angle, we have to make the camera tilted to get the whole motion of the water bottle rocket. So we also did the correction of camera angle. And these are the prerequisites for our assumptions. So first, how are we going to define successful launch conditions? So we think that we define successful launch conditions as the water jet phase needs to finish before the rocket reaches maximum velocity. And second, we assume that the water is incompressible. And also the bottle doesn't change in shape or size. And we also think that air expansion at any time is considered as an adiabatic process. And here comes our experiment. So in our first experiment, we want to find the relation of acceleration over time to air pressure. So we change different air pressure from 20 pounds per square inch, 40 pounds per square inch, 60 pounds per square inch to 80 pounds per square inch. And this is a result of our experiment. So here we can see that the acceleration is positively correlated to the air pressure, as we can see that the different lines represent different air pressure. But however, the trend of the acceleration is pretty different, and this is what we're going to discuss later in our experiment discussion. And also, in the same graph, we can see that for 20 pounds per square inch, there is an obvious deviation between our experiment data and our theoretical data. And this is how we've observed that this is an unsuccessful launch because the water jet doesn't finish before it reaches its max velocity. So we want to find why it doesn't fit this theory. And we think that it is due to the change in direction of total force because the water bottle rocket is not always in the vertical direction. So if there is an obvious change in the direction of the water bottle rocket, we can see that the air drag force would be different because the cross-sectional area of the water bottle rocket would be different. And here we also get the velocity over time of the water bottle rocket for 20 pounds per square inch. And it looks like this. So we can see that due to the increase in the air drag force, the velocity over time doesn't fit our theoretical line. And this is also why it is an unsuccessful launch. And we're not going to discuss this in our later experiments. And for our second experiment, we're going to change the water volume from 120 milliliters to 360 milliliters. And we can get this experiment data over here. So for different lines, it represents the different water volume. And we can see that the acceleration is negatively correlated to water volume. And this is very reasonable because if the water volume is bigger, the mass will be bigger and the acceleration will be smaller. And we can also see that our experimental error is always within the 5% range. And we also did different water volume for different air pressure. So this graph is different water volumes for 80 pounds per square inch. And this is different water volume for 20 psi, 40 psi, and 60 psi. And we can see that it all follows the same trend that when the water volume increases, the acceleration will decrease. However, the pattern of the acceleration over time is actually pretty different. So after all of these experiments, we are going to classify the trend of the acceleration into 4 different types after observation. And this is the first type, which is in the accelerating phase, the acceleration always increases over time. And we think that the change of the trend of acceleration is due to the change of the thrust, which is the total force, and the change of the rocket mass over time. And since these two are different, they will cause different trends of acceleration. So this is the first type. And the second type is the acceleration first decreases, but then it increases, and it is bigger than the initial acceleration. This is type 2. And this is thrust over flight time and mass over flight time for type 2. And for type 3, we define type 3 as the acceleration decreases and also increases after, but it is lower than the initial value. And this is a change of thrust and total mass over time for type 3. And this is type 4, which is when the acceleration always decreases. And this is also the change of thrust and total mass over time for type 4. So if we put these conditions into our simulation data, we can find the boundary conditions of each type. And after it exceeds the limit for type 4, it will be unsuccessful. And these are the range for different types of trend of acceleration. And this is different trends for our experiment data. So we can see that for different sets of air pressure and water volume, the type will be different. And if we put this into this graph, which is water volume to air pressure, we can see that our experiment data will fit in this graph, and it's always makes sense. And here comes the conclusion of my presentation. So first, in the theory, we discussed about the acceleration process, which is divided into water jet phase and air jet phase. An air jet phase is considered as an adiabatic expansion. And the thrust, which is the force given by the water or the air, the air drag force and gravity are all considered into our acceleration. And our definition of a successful launch is that the water jet phase finishes before the rocket reaches maximum velocity. And this is the conclusion in our experiment. So for our experiment, the change in direction of the total force causes a greater air drag force, which will cause an unsuccessful launch. And we are not going to talk about unsuccessful, which we won't consider in our experiment data. And the water volume and air pressure affect the acceleration simultaneously. So we classified into 4 types of acceleration trend for different water volume and different air pressure. And the boundary conditions for the 4 different types can be found by simulation. And our experiment data also fit these classifying of types. And the water volume and the duration of jet phases are positively correlated. And the air pressure and the duration of jet phases are negatively correlated. And this is the end of my presentation. Thank you.
Another 2 minutes. Okay, thank you for your presentation. Do you think the water flow during the water jet phase is laminar?
I think that there might be some turbulent flows, but it is included in our error.
So you think that the whole water jet phase is turbulent flow?
No. There might be some turbulent flow, but it is still mainly laminar.
Okay. Does the water remain in the rocket after launch?
Sorry?
Does the water remain in the rocket after the launch?
For the water jet phase, yes.
How many trials have you done for each measurement?
We did about 5 to 6 times for every data.
5 to 6. Did you do the experiment in the same state, like the same weather? Has anything affected the? What do you think? What are the factors that affect the direction, the trajectory of the rocket?
I think that the factors that cause the trajectory is total force given by the water or air.
Which parameter do you think would affect the acceleration the most?
Sorry?
Which parameter, when you change it, do you think affects the rocket the most?
I think that it's both the water volume and the air pressure, because we classified it into 4 different types, so both of them will change it simultaneously.
So wait, can you say why you think the direction of the rocket changes during the flight?
Because the force given by the water is not enough, so the airflow is relatively unstable.
Do you think the flow of the air in the air jet phase is unchoked or choked airflow?
Sorry?
Do you think the flow of the air during the air jet phase is choked or unchoked?
How do you define choke or unchoke?
Oh, never mind. So okay.
太难。
些图是比较浅色，可以帮我们把那个投影机调亮度暗一点嘛？因为亮度太亮会。
左边那一台。
对，我们 report 那一台。 会有些数据看不到，所以看可不可以把亮度调低一点。
好，我就调低一点。
谢谢，麻烦了。
控茶。
Okay, taste the broth. 14 minutes.
Honorable judges, fellow participants, and most esteemed guests, I admire you from known nighters and we'll be talking about the water bottle rocket. So the problem statement states that when you pump air into a plastic water bottle partially filled with water, under certain conditions, the bottle is launched and flies into the air. Investigate how the acceleration during liftoff depends on relevant parameters. So my ideal structure of investigation is pumping the plastic water bottle with the air and water, investigate the acceleration during liftoff, predict the pressure versus acceleration, and adjust parameters. Now the structure of solving the problem they had was that they calculated the force using mass impulse phase, and they split into water flow and airflow, the water jet phase and the air jet phase. And then they pumped air into the bottle with the rocket and they tracked the trajectory. And they compared pressure versus acceleration and determined the critical points. Now the pros and cons of the report. Some pros that they have good grasp of visuals, good pacing of presentation, and had a clear, loud voice. Cons, however, they didn't have enough phenomenal understanding, blurred diagrams for experimental setups, and not enough explanation for all observations. So the task with movement is partially. Now, moving on to the points of discussion, we wish to discuss with them to analyze the falling phase of the rocket, how the air mixes with water during the phases, and the reason behind their adiabatic expansion, not just an observation. The water volume, how water volume negative correlates with height. And I would like to invite the board members. First discuss the air mixing with water. Do you think that as water goes out, the air could mix with the water, making the water flow turbulent?
Yes, I think this is one of a minor component of our error, and we think it's because the way we measure our pressure after, instead of after we pump air inside, we have a scale that shows the pressure inside the water bottle rocket, and we think the pressure is after the air mixes with the water. So we think that our pressure is controlled, and we don't consider that the air mixing with the water would be. We think that it is neglectable.
So, and the way you track the trajectory of the rocket was, is it correct that you only use a phone to just video and see what's happening? Did you use any
A
specific
slow motion camera.
slow motion camera? So there's no specific tracker track the trajectory of the rocket.
Oh yeah, of course we did use tracker to track the trajectory.
Now, I'll talk about the reason behind the adiabatic expansion. You talked about it. You just state that there is no heat loss into such a fast reaction. Is there any scientific or mathematical reason you
Yes, so we mentioned this is our assumption that this is a diabetic process. And so from this equation, we did actually, in our simulation, calculate the PEV to the power of gamma is always the same.
Okay. And can we talk about how you think the water volume negatively correlates with height? Can you further explain how you think so?
No, I think you have been misunderstanding on this. It's not negatively correlated with height, it's negatively correlated with acceleration.
With acceleration. Yeah, and then you described the 4 types of acceleration, and you talked about the observation. Can you explain why these 4 types of acceleration happen?
Yes, so for the first type, which we define is that the acceleration always increases until maximum value. So because f equals to ma, so we want to find why the acceleration will show this trend. So we also, this is f, and this is the mass over time. So after this trend, like dividing f over the mass, we can get the acceleration. So this is a result of these 2 data. So for the different trend of these 2 data, they will cause different trends of acceleration over time. And this is why we are going to classify it into 4 types.
You said can you describe the factors that affect the rocket trajectory as you took? You said you wanted to use a launch pad to have only vertical movement. Why do you think it has the moves in the other directions?
I mean, what I said is the launch pad we use that like we made sure that every time we launch the rocket, it is always in the initial angle of 90 degrees to the ground.
And always goes straight up and doesn't move in any other direction.
If it moves in any other directions, then we'll regard it as unsuccessful launch.
Have you considered conducting a grounded experiment instead, especially the thrust of the rocket?
Sorry?
A grounded experiment, like. So I would suggest,
I mean, you could make the rocket connected to like a chair or something, and then you use a kind of gun, air pump air to it, and then you have the nozzle here. When you release it, you can measure the thrust without any other practice.
I think that we don't have the need, there's no need to measure the thrust because we actually have this in our simulation data. Like we don't need to do an experiment for this. I don't think.
Can you talk about the falling phase of the rocket after the water jet phase?
After the water, the falling phase. Yeah. So after the water jet phase and air jet phase, there is no more upwards external force acting on the rocket. So the rocket will only experience gravity and air drag force.
Okay, what potential errors do you think have to do with your experiment? What errors do you think caused by that? What errors do you think are relevant to your experiment?
I think that the errors of my experiment are caused by, first of all, tracker is one of the main errors that we think it is, and also you talk about the different airflows and different water flows. So maybe some unstable water flows or airflows will affect the error, but I think that it is negligible.
And, okay, and you said that I saw that in the video, you conduct the experiment in the outside, in the outdoors with weather. Do you think that the surrounding state can have an effect on the trajectory of the rocket and
This is the what state?
like the weather outside?
Oh, the weather state. Well, I think that it only holds a minor effect on our experiment because we did try to do it in like when it is the wind speed is very small, so that it doesn't affect the rocket.
Okay. So you don't think that despite sunny weather, with the temperatures hotter, then the molecule's velocity moving faster, there will be more expansion. You don't think that would account for anything in your experiment?
Yeah, because we observed that the air jet phase is the time of the air jet phase is very short, so I think that there will be not enough time for heat exchange.
Can you talk more about the laminar, non-laminar, and turbulent water flow and water jet phase. Do you think that these boys non-laminar flow, do you think they're phased towards laminar or non-laminar?
We actually didn't analyze, like, because it is very hard to observe if it is laminar or turbulent or like non-laminar. So
So you just assume that it's laminar, or do you assume anything about the flow of the water?
well, I think that at the nozzle, the water should be laminar flow, but the main reason that it will cause the force to the rocket is at the nozzle. So I think that this doesn't actually matter a lot.
Okay. Can you go back and go to the page with your equations on the thrust of the rocket?
This one?
Yeah. Okay, I have a question. So the rocket is like this with water here and there. Do you think that the water could act as a seal and make sure that the air doesn't mix with the water, and that will make the flow more laminar?
Well, I think that the air will still mix with the water, but it is not a lot. Like the saturation of air into water is very small, so I think that it is negligible.
Okay, so what effect do you think? So you don't think the air mixing with the water will have any effect on the rocket's acceleration or trajectory?
It will have some effects on our result, but I think that is included in our.
Can you describe what effect it would have on, like, if you were to observe it, what effect would the air and water mix have on the water?
I think that it only causes some difference in the source of the water, but again, it is negligible.
Can you? I don't think I've heard listened to this about your linear technique. Can you describe exactly what forces contribute to the rocket moving upwards? Do you think that it's because as you release the clamp, there is a velocity downward by the water, so there's momentum downwards, so to conserve momentum, there's a momentum moving upwards as well. So the whole rocket as a whole moves upward.
I think that the main reason that will cause the rocket to have an acceleration upwards is that the thrust is bigger than the air drag force and the gravity.
Okay. Can you move to page 13? I think.
This one?
Go right next. Okay. Can you describe what is happening here in the graph?
Okay, so in this graph, the scattered dots are the experiment data for different air pressure in different colors, and these are the theoretical lines for different air pressure.
So what do you think are the most crucial parameters to maximize the acceleration of the water rocket?
That's acceleration.
Yeah. What do you think is the most best parameters to have for the water rocket to accelerate the maximum?
Yeah, so I think that actually the acceleration will change over time. So I think that we have to discuss about the different types. So if you want me to find like the best initial parameter for a very high acceleration, I would say that somewhere in our experiment around 80 psi and maybe 400 something milliliters of water volume would have the best acceleration.
Okay. Can you go to page 18?
Here.
Oh, yes. Go back. Go back. Okay. So the cross-sectional area changes in drag force. Do you think that that's a more important part? What do you think affects which phase do you think the drag affects most? The water jet phase or air jet phase?
Water jet phase, because since it's an unsuccessful launch in our definition, there's no air jet phase for an unsuccessful launch because the water jet phase doesn't finish before it reaches its maximum velocity.
So do most of your trials happen under the same conditions? Like have you considered airflow and other factors into?
Yes, we said that we did it in the like outdoors, and we tried to control that there is only local effect on the wind
So you
and also the temperature.
So how many? So you have done many trials during like one state of surrounding.
Maybe we cannot always control the like totally the same surrounding every time, but we can like try to minimize the effect on it.
That's it. Thank you.
Thank you.
Okay. Let me summarize the discussion.
So the reporter and I have discussed many subjects in our discussion, including the air mixing with the water, and he states that it could contribute to the air as it would make it more turbulent, but he thinks that it's not big enough to greatly affect the calculations. And they find that it's negligible, and for unsuccessful launches, the reporter thinks that the cross-sectional area has the biggest change. And for the experiment, which has a more accurate way to measure the thrust by using like a grounded experiment, and to measure the force more directly and less affected by other factors like the airflow and the surrounding state. And we suggest a more direct comparison to force instead of simulation. And Eric's experiment, we agree that different airflows and different water flows affect the experiment.
Okay. So that means review our question.
In the cover statement answer to investigate the acceleration during liftoff, can you define what is the liftoff in your experiment?
In our experiment, lift-off would be the water jet phase and the air jet phase.
So, do you think like the phase 2, because the water is fully ejected still in the conditions of liftoff, like you already finished ejecting all the water. Does this condition still in the process of liftoff?
Yes, because there is still air expansion, which causes a
How
stress.
about the opponent?
Can you say your question more consistently?
Like, do you think when the water is fully ejected, this phase is still in the process of lift off?
No.
No. Okay. What's the reason?
I believe that liftoff is when we release the bottle from the ground.
So it's in a short time, right?
Yes.
Okay. Thanks. How do you think the turbulence will affect the phenomena?
I think that it has a negligible effect because the stress is caused by the water pushing out at the nozzle.
That causes deviations, right?
But very small.
Very small. Do you agree with the?
I agree that there would be a difference, but then because it would affect many of the calculations you use in your experiment, like the equation where they were calculated thrust by using the area of the water coming out, that would change because the air would mix with the water.
So, okay, thank you. How do you think the pressure changing speed of the water rocket will be different when the water volume is like different? It isn't the same. Like the speed of the change, like you use the adiabatic process, right?
Yes.
Then, so the pressure will change in the water bottle rocket.
Yes.
And do you think the changing of the pressure changing speed will be different in different conditions?
Yes, we do observe it in our experiment.
So can you like with bigger water volume, what's the speed compared to smaller?
So I guess what you want to say is the duration of the air jet phase, right?
No, it's never mind. How about the opponent?
Can you restate your question?
Okay, never mind. Question for the reporter. Did you find out the critical condition of the pressure in your experiment? Like, is there a minimum pressure that the water bottle rocket won't launch? It's not like your.
Yes, so for different water volume, we have different critical values of pressure that will launch, which is the boundary for a successful over here.
Okay. How about the opponent?
This is his data. I wouldn't.
Okay. I believe there will be like it have to conquer the friction or other thing to agree that like the friction between the launcher and the nozzle.
Time up.
Honorable juries and fellow competitors, I'm the reviewer from Team Excelsior. Today I'm going to review problem number 14, water bottle rocket. Here's the problem statement. Today I'll mainly focus on under what conditions the bottle will lift up and what parameters will affect the acceleration. So here's the review for the report. They use the theory of conservation of momentum and the Bernoulli's principle, also the adiabatic process to describe the phenomenon, and they also consider the air jet as a very important theory. And for the experiment, they have two parameters, which is the pressure and water volume. And the reporter did well on providing like demonstrative explaining the phenomenon well and have a clear explanation of the theory. But however, they didn't have a clear observation video of their report, and the chart is not clearly marked that we cannot see the unit of it. And they didn't have, okay, and then is a review of the opposition. The opponents noticed the lack of the explanation of the deviations, and they discussed it, and also they discussed the boundaries of the experiment. However, they failed to discuss the lack of the experimental setup, they did not discuss the retraction index, and they failed to notice the lack of parameters, which is only 2. And then let's move on to the key discussion. For the parameters, the opponent asked which parameters changes the experiment the most. The reporter thinks it's the water volume, but the reviewer disagree with the reporter because we think the pressure is the main effect during the lift-off process. The water water volume only affects the mass in the lift-off process. And then it's the direction. The opponent asks why is the direction of the rocket changes during the flight. The reporter thinks there might be instability caused by not enough force of the water and air in the rocket. The reviewer thinks that the reporter should only include the conditions with the rocket only flies completely vertically. And the opponent asks, does the reporter think that the water will mix with the air and cause deviations? The reporter thinks that will happen when the water inside the rocket is less, and we will agree with the reporter. And next is our question. The opponent didn't answer this question of about critical condition, while the reporter thinks they are already mentioned in the report. And here's the definition. We asked the reporter to define what's the definition of lift-off, and they said it's their answer is the water jet phase and air jet phase, while the opponent thinks the lift-off process should be shorter in time. And here's the point: is for the theory part, they didn't consider the friction effect between the nozzle and the launcher, and they didn't consider temperature rise since they didn't use the adiabatic process in the phase 1. And for the setup, they didn't have a clear other external forces or disturbance. And they didn't discuss the trajectory after launch, and they didn't discuss the falling phase of the rocket. They didn't discuss the air mixing with water enough. They didn't have a result. Thank you.
Concluding remarks. 2 minutes.
Okay, thank you for the opponent and the reviewer. And this is the concluding remarks. First, for my report, the acceleration changes to time, and the trend of acceleration can be classified into 4 types of change due to the change of the total force and mass. And the water volume and air pressure affect the acceleration simultaneously. And boundary conditions for the 4 types can be found using our simulation, which is shown in our graph. And for successful conditions, our experience data fits our theory data. So other error factors can only hold a minor effect. And this is a concluding remarks for the discussion. And The opponent asked about the unstable flow, and we think that the unstable flow only has minor effect on acceleration since our experiment data actually fits our theory data. And also the thrust only happens at the nozzle, so we don't think that the unstable flow after the water is pushed out is, we don't think that it matters a lot. And we think that the lift off is the whole process of the acceleration phases, which is water jet phase and air jet phase, not only the moment when it launches. And for successful conditions, the experiment data fits our theory data. So other effects in error, such as what we talked about, unstable flow and also some other deviations, I think that the error is very small, so it can be neglected. And for unsuccessful boundary conditions, we can find it through the boundary condition from our simulation data, the line between type 4 and successful area. And we do have a theory line in our diagrams. And this is a concluding remarks. Thank you.
Thank you. Any question? Yeah.
Okay, so for the reviewer, you talk about the friction.
Yes.
So you think that is the one of the most important part?
We think that it is related to the critical conditions. We think when the pressure inside the water bottle rocket cannot conquer the friction between the launcher and the nozzle, it will not lift off.
So how
I think it's negligible because I don't think it has a big effect on the speed. So
I agree with the opponent. I think that the friction is relatively small compared to the thrust of the water or air, so I think that is negligible.
So another question is for the opponent. So what is the most critical, I think, parameter you think they can have?
can you say your question?
I mean, what is the most important parameter you think they can add in this experiment?
I think they covered really important parameters. Have they changed the bottle size? I think important parameters are bottle size, volume of the water, and the pressure of the air. And I think they cover most of that.
So
We also think the most important parameters is the bottle size, because the bottle size will affect the changing speed of the like with the bigger bottle size, the pressure change in the water bottle rocket will be minor, and if the bottle size is small, the changing of the pressure will be bigger. So we can I think the reporter can consider the speed of the water of the pressure by having a new parameter of the bottle size.
We didn't do bottle size in our experiment, so I think that the water volume and the air pressure are both dominant factors on the acceleration. And yes.
So I have a question for all of you. If you, in your rocket, water rocket, and you fix the volume of the water, then you just change the pressure. Okay? So if you want to the rocket fly to the highest point, what's the best pressure you will get at?
Yeah, so if let's say we control our water volume, right? If we fix our water volume,
Yes.
so we're going to see for different air pressure. And I think that the best air pressure will be as large as I can,
Larger.
because the type 1, type 2.
Keep larger?
Sorry?
If you reach the highest point?
In our experiment, we only did to 80, so we don't know like the
Beyond that.
yeah.
How about?
Oh, we actually believe the most important factor in the acceleration is the water volume. Because we believe that with more water volume, there's a higher seal, and we don't have
I only change the pressure.
only
So
change
the
pressure. I believe
water volume is fixed.
the higher pressure would be better.
The highest pressure.
I think when the pressure drops to 1 atm and the water is fully ejected from the water bottle rocket, like when the water bottle rocket's water is fully ejected, and also the pressure drops to 1 atm will be the perfect like ratio between.
So you think
It's-
that's
it's-
optimized pressure?
And
Or
there will be a
peak?
there will be optimized pressure that because if you increase the pressure like if to infinite it will the water will eject too fast that it will be only ejecting air and
Understood.
I'll let you back my answer. I agree. Okay.
Can I ask one short question for the reporter? So I wonder, do you measure the temperature change inside your water?
No,
When
but
the water all throughout, in beginning and after,
yeah,
you measure the temperature.
no, we didn't. It is hard to measure the temperature change. So we calculated the P times.
I know that.
And it's also constant. So if
Do you see the temperature change a lot?
no, not really.
Then why you use this? Now just use the temperature almost is constant, and just PV is constant. So why you use the diabetic?
But at the diabetic, because
The temperature will change.
yeah, but there's no heat exchange.
But the no, your inside your environment, the temperature will change. If it changes,
Oh, you're inside the
Yeah.
bottle. Oh, yeah, yes,
When
yes,
you
yes,
use this
yes,
equation.
yes. Sorry.
So your using equation means you assume that the temperature is not constant inside the rocket.
Oh, yeah, inside, right, yeah, it is not. The
So-
temperature is not constant, but PV to the gamma is constant.
So you're trying to, I don't know, maybe you can try to measure that it difference. I don't know how about you guys' opinion about the using this equation. The temperature is not constant.
the reviewers can suggest the reporter to use like Arduino for like sensor to like make sure the temperature would change or not change. So it's like it will be a better.
Have you tried that? You change or not? Have you tried this? The temperature is constant or not constant?
It will not be constant.
It will not be constant. How big the difference?
Yeah.
太大。
我想，I think it's okay. Not too much.
Thank you. ก็ reporter. Eight, 6, 9, 8. Or 7, 7, 7, 6, 7. Reviewer. 7, 6, 7, 6, 7. We record this session and this stage. Take a break. You can after 10 minutes, okay?